Yeah, today I'm without a microphone. I hope I'm going to be audible enough. Yep, that should work. Should be fine. All right, so let's just briefly remember. So let's think about hypothesis testing. Essentially, we are testing now the distribution of the sample. So the use case is we have one sample of a certain size, and we're utilizing the information from our population for a STAT test. We're utilizing the information from a population, which is the standard deviation, to estimate based on the size of our sample and the standard deviation from the population, the distribution of our sample means. So thereby we're creating an hypothetical variability. Yes, please.
Did we discuss the image quality?
Yeah, kind of. What would you like to discuss about?
Oh, I'm just wondering what you think is important to learning, or what.
Lecture recordings, the chapter in the book, 1 to 8. Utilizing practice quizzes to test your own knowledge. It goes through the examples.
And the format, sorry, I don't know, I know they mentioned this in the class, but just to clarify, the format of the questions is just like the quiz.
The format is going to be comparable.
Like the quiz.
Comparable.
Meaning, so not like.
Comparable. So let's put it that way. There won't be no quiz format where you suddenly have to calculate the most difficult things. But you will be asked to calculate, for example, set scores, p-values. So these things may be coming your way, or you may be asked to go into the question and extract information independently, calculate confidence intervals. These things could happen to you. There's not going to be hardcore, very difficult kind of calculations. You don't have to submit Excel spreadsheets. There's going to be solvable problems which you will find in the lecture material. To some extent answer. You just need to know how to go.
So just the same questions in what, as in what?
They are the same questions in the lectures. They are the same questions as you find them in the practice quizzes.
Oh, yeah. So like the practice quizzes with. Are we?
Well, they're definitely helpful to test your own knowledge. Yes. But the knowledge needs to come from somewhere else. So the practice quizzes alone are not. All right. That is a paper experience. Some of the practice for it.
Oh, good. Are we also able to have a formula sheet?
You can have your own notes. Yes.
It's open.
Open notes. Yeah. But again, I would like to emphasize no messaging, no grouping. You can have open notes. So you can have your own notes open on Google Docs or whatever. That's fine.
So you would say if we went through the lecture problems, the quiz problems, we would be mostly good. We
Lecture material and the lecture recordings, I would read the chapter. I highly recommend it.
What do you think? Does the chapter in the book explain more processes, or is it just more history?
It gives you what it may give you is different examples. And explain in more detail ways. We're looking at these examples, but explaining with my viewers how to look at what I'm showing you on the slide. The book may present it differently, so I'm not reading from the book. I'm not explaining it in the same way. I'm explaining it how I think it's easily understandable. It's going to be 25 questions. You have 1 hour. So I'm deviating a little bit from the 30 or 2 minutes per question approach that they usually have, because I've added more shorter essay questions.
And you can have Excel open.
I would encourage you to do Excel and find with a calculator or whatever you do on hand.
Okay. Module 11.
No, it's up to module 11, yes. So chapter 1 to 8.
Yeah.
Yeah.
Your module 11.
Exactly, yes. Any other questions? Good. Okay, so I think also keep in mind all 8 chapters are going to be somewhat equally distributed. in the quiz questions, but the emphasis is kind of in hypothesis testing and confidence interval naturally, right? Because this is really where statistics begin. And okay, if no further questions, then let's talk briefly about confidence intervals and hypothesis testing. So keep in mind that we are doing hypothesis testing on the distribution of the sample means, and as opposed to what we have done in the population, where we standardize a population for the individual scores, where we capture the number of scores within a certain region. Now we're basically determining within the distribution of the sample means the boundaries amongst that variability. So essentially what this becomes now, the p-value or the probability or the percentage that we find from the distribution table is essentially now a probability and not a percentage of scores anymore. It could be considered a percentage of sample means. That would be a possible thought approach, but it's easier to think of it as probabilities. So essentially, you're quantifying the probability based on the distribution. You're quantifying the probability that that mean that you have is essentially identical to your population mean. So on the tails, you have the probability that actually a mean that would correspond with a value somewhere that far out here would essentially be more extreme than what you would expect from the distribution of the population. So that's why it's important to standardize it according to the population standard deviation and have an estimate of this variability of the sample means. So you're deriving that from the standard deviation of the population, under the assumption that if you sample from something that is very widely distributed, you're more likely to get more variability in your sample and in the distribution of the sample means. That's the idea. So we have discussed the critical values. We have discussed 1.96 that basically fills and defines an alpha divided by 2, so a half alpha of 2.5% on both sides. And then we have also discussed 5% on each side, which is a 90% confidence interval, which essentially is at it's basically at 1.65, and then we have 2.58 for the 99% confidence interval. So again, the narrower it is, the less likely I'm capturing that population mean. So think of that. It's the probability that the population mean is actually inside of these confidence intervals. So smaller is narrower on that set score. And you see that on the actual spreadsheet that I have posted and that we have computed last time. When you look at the spreadsheet, you see this clearly represented here with these three confidence intervals. You see that 95% you have 514 to 569. You have 90 with 518 to 565. So that's clearly narrower than the 505 to 578. That's wider. So you're more likely to capture the population. So if we're going now in that example, so we're doing that example now a little bit more in detail. So this is again 729 and 730. So I want to go through this once again, because today we're going to add an additional dimension. And what we're adding today is now our left-sided and right-sided, one-sided set test. So let's remember the cholesterol example. So we have a subset, a sample of 25 hypertensive smokers, and we're comparing their cholesterol against the population mean. We had a population mean of 211 milligrams per deciliter, and we'll yes. Yes, I'm recording. Oh. Yes. Okay, now you make me insecure. Let me think. My screen isn't showing. Still not?
It is. It showed that.
It must be showing. It should be showing based on what I'm seeing. So I am recording, thanks for asking. So it should be, the screen should be on. Good. Okay, so we have cholesterol now. We have a two-sided self-test. We are again calculating this in the formula as we have discussed previously. We have X star minus the mu that constitutes or calculates the difference between the sample mean and the population. We're dividing this by the sigma divided by the square root of the n, which is the standard error of the mean. Again, that's the variability of the distribution of the sample means. So arithmetically, this is basically 195 minus 211, which is minus 16. So we know from that already it's a negative set score. We're dividing this by our set score, but by our standard error of the mean. That gives us a set of minus 1.74. If we're going now in the distribution table, where should we find that? If we go in the distribution table minus 1.74, we find 0.0409, which is our 0.041. But again, keep in mind it's a two-sided test. Therefore, we need to multiply by 2 to account for both tails. Gives us 0.082, more than 5%. And we're
I'm confused like how you're supposed to use that table. Like how do you know
okay. Thank you for asking this question.
which side to go down? Like what are
Yeah,
the,
this.
like,
Yep.
what are the top so
So we have rows and column. So the rows basically identify the absolute number before the comma and the number after the comma, so the first decimal. So 1.74 is here minus 1.7. And if I want to know the second decimal place, then I click on the column, then I go all the way down until I'm at 1.74. So this is 0.041. Make sense? Good. So this is our example now. And what's interesting now, when thinking about one-tailed hypothesis test. So one-tailed hypothesis test is different, and you only use one-tailed hypothesis when you have a hypothesis direction in your research question, which is not often the case, but in some certain examples, you may get away with it. The advantage of a one-sided test is that it doesn't consider both tails, thereby the p-value is going to be smaller, which is an advantage to some extent if you want to reject the null hypothesis and in the case of a directional hypothesis. So here, that example, and this is where it's important that you know how to express null hypothesis and research hypothesis, because the research hypothesis will lead you to the definition of your normal distribution. So you will know in which direction you're testing. If you have two tails, you're counting the p-values on both sides. If you have only one side, you're basically testing below this value. So therefore, you're only counting everything that is less than that cutoff. So in this example here, we're basically calculating 195 minus 211. We're dividing this by the standard error of the mean. We're back by that set equals minus 1.74. And now we're not multiplying it by 2. We are at a p-value of 4.1. Important is that keep in mind that your null hypothesis here is that your sample mean is greater than your population mean. Yes, greater either.
When you say one-sided versus two-sided, it's basically just to see if it's a negative or positive.
That it is greater or smaller, yes. So your null hypothesis is now not, its sample mean is equal to the population mean. Now your null hypothesis is that the sample mean is equal or greater.
Okay.
So you're taking equal and then everything above, that would be your null hypothesis. Everything below that population mean would basically be your research hypothesis. So when you do it the other way around and your one-sided hypothesis says now that under the null hypothesis, your sample mean is actually smaller or equal than the population mean, 200 milligrams per deciliter, then your research hypothesis is basically that the sample mean is greater than 211 milligrams per deciliter, which now puts the emphasis on everything above that critical value. So everything greater than 1.74 minus 1.74 SAT score. So putting this now into, let's copy this over. And I'm just copying this now in that spreadsheet with a little bit of a back thought here. And this is why it's important to sketch out that normal distribution curve, because by doing that, you're helping yourself a little bit. So let's assume again we are this one. Let's assume again we're doing the example from last class. And I'm not really sketching it, I'm showing you this way. Okay, so 7.29. If we go on the PowerPoint presentation with the examples, we have now you're conducting a SAT test on a sample of 50 people. And it's the same example, we've calculated it already. But for the sake of simplicity, just to walk again through that. So we have 50 people in our sample. We have a sample mean of 542, and we have a population mean of 500 and standard deviation of 100. We have a sigma of 100. We have a mu of 500, that's our population mean. We have an X bar of 542, and we have an N of 50, right? 50. Yeah. So now it's considerably simpler to formulate the null and the research hypothesis. So we know it's a sample of 50 people, it's 50 students. We know the mean, and we kind of have an idea what the distribution is. We could calculate right away the standard error of the mean, which is basically our sigma divided by the square root of our sample size, which we remember maybe from last time is 14.14.
What do you do divided by the square root?
Square root of 50. Yeah. If we are now phrasing the null hypothesis, that would mean that X bar equals our mu. The alternative hypothesis, X bar is unequal to mu. So exclamation mark equal sign, so that's a coda thing. That's basically how you express it's unequal to. So those of you who are going into computer science will see that maybe down the road. Okay, so we know two-sided test, it's identical or it's not identical. It's either greater or it's either smaller. Our alpha is 0.05. Let's assume, oops, it's 5%. Now we want to know our SAT, and the SAT is, as we remember, it's calculated as our X bar minus the X divided by our standard error of the mean. So we know already, and we remember that probably from last time, that's the null hypothesis we had. That's the SAT we calculated last time. So
You copy the equation.
Yeah. Sure. That's B3 minus B2. So in a two-tailed hypothesis, our null hypothesis is here, F4. Our research hypothesis is F5. So this is how we fill out this table, right? So now our SAT is contained in here. It's 2.96. And now we need to calculate our P, and that P is basically the P where SAT equals 2.97. That's the P I want to have. But it's basically that P multiplied by 2. So this is how you have to think of it. So if you are calculating, that's actually, okay, then I'm making a mistake with the following. So if I'm going now on 2.97 plus 2.97, 2.97 is right here. This is here 0.9985. The difference is 0.0015. So I'm going into Excel. The P is now equals 1 minus 0.9985 multiplied by 2. So that's our P. So now clearly I can see already the probability of this coming from the same distribution and the null hypothesis true is smaller than 5%, which is my defined alpha. So I'm going to be rejecting the null hypothesis. So now you can leave this as a proportion, which is 0.03, or I can multiply this into a percentage by multiplying this by 100. It's still 0.3%. So nothing changes. And if I want to bring this in the format that I express this as, that's actually X bar. So X bar is 542. If I want to calculate this as a confidence interval, I would calculate 542 minus 1.96, because that's our critical threshold, that's our critical set, multiplied by standard error of the mean. So that's 514 again. Or alternatively, I take 514 plus 1.96 multiplied by 100, 14.14. So that's 569. So that's the 95% confidence interval for a two-sided hypothesis. So now we're getting a little bit to the more complicated part. So now we have a one left-tailed hypothesis. So let's keep in mind, what is the null hypothesis of a left-tailed hypothesis? That's the first one. There, our null hypothesis is the opposite. So this constitutes the research hypothesis. That means our X bar is smaller than our population mean. So this is here indicated. So we know now that this would be the null hypothesis. That's X bar is smaller than mu. The null hypothesis is the opposite, where we're saying X bar is greater equal of mu. So that's the null hypothesis. If I want to calculate a set, the calculation is identical. Calculation is the same, so we're taking the same set. The difference now is that our P is not multiplied by 2. But it's basically 1 minus 2, what was it, 0.9985. So this is our 0.015. 0.0015. So now we have, again, a significant difference, but it's substantially low. It's only half of that what we have on the of a two-sided test. Now we can, obviously, we can make this again 0.15, that's 0.15. If we do the opposite now, and we're doing a right-tailed one-sided hypothesis, we're doing X bar. And for you, it's important to understand how to derive to this. X bar equals mu. And the formula is X bar greater than mu, because that we're interested in. So we have now again 2.9. We again have this. That's our set. And now we're basically calculating. So now we're interested in everything greater than this extremely large set value of 2.987. What's my mistake now? So That was bad. Okay, I got a little carried away here. So X bar greater than mu is our null hypothesis. X bar smaller than mu. Okay, so back. Sorry. This is actually positive volume. So we are not calculating 1 minus 0.998. And please don't be confused now by this. Okay, let me explain. My bad. My bad. So if we're calculating X bar greater than mu, and the research about X bar smaller than mu, your research hypothesis is actually 0.9985, because that's actually the research hypothesis that we're looking at, because it's a positive value. I got in my head mixed up because there's a negative. So you need to calculate the direction you're actually testing. So we're testing everything below it, but in essence, that below it was actually here. So this is why it's so important to sketch out the normal distribution curve, and I brought it just to the test why it's important to sketch it out, because you get easily caught up. So we're testing by calculating the set. We're getting a set score. This set score essentially represents our critical value, which is somewhere here. Now, our null hypothesis is X bar greater than mu. So this is actually 0.015, because we're not doing two-set. So now everything below that is actually our null hypothesis. So our now everything below that is actually our research hypothesis. So the research hypothesis is now 0.9985. Yes. It depends on the hypothesis that you want to test, right?
No,
Because you focus on the research hypothesis. If you say X bar is greater and the research hypothesis X bar is smaller, the research hypothesis actually determines which area you're interested in. So if you're interested in everything smaller than your critical value, then you will quantify this as your p-value. That's your probability of this actually being smaller.
meaning from the other side.
Correct.
And if you do it vice versa, you would have to do from the lower side.
Exactly, but it's a definition that you basically pursue. And since the set score is so extremely large, there's actually very little probability of this being significantly different, or not being significantly different in that direction.
Right.
Because we know that X bar is actually substantially larger than our mean. So we know the null hypothesis to be true, because it's 542 versus 500. So that's where you need to think, what are you subtracting from what? So you're subtracting 542 and you're subtracting from 542 500. So you know already that there's a very large difference. So
not large.
that's where
Not a large difference.
No, it is a large difference. It's 42. That's almost like 10%.
Oh, okay.
It's 10% larger. So that's where the trick is. I tripped over it. Yes. So yeah, then yep, happens to the best of us, I guess. Okay, so we have 2.97, we have 0.9985 under our research hypothesis. So we know that our X bar is it's less likely to be smaller than mu. So now this obviously is now this is this, and this is multiplied by 100. Okay, so now we're actually getting to that example that I meant to show before. So if X bar is smaller or equal to mu, under the null hypothesis and under the research hypothesis, we are testing. So this is our research hypothesis. X bar is actually greater than mu. Yes.
Shouldn't be, I think that's 20 be 3, not 0.3. Shouldn't be 20 be 3, not 0.3?
20.
Like be 20 the box.
0.03.
Shouldn't that be just regular 3, not
No, if you multiply 0.003 with 100, that gives you 0.3. That would be multiplying by 1,000, then it would be 3.
Oh, okay.
Yeah,
Thank you.
just one moment, that's me. Okay. So after this little hiccup, so we have now x bar smaller equal than mu, and x bar is greater than mu. So we are quantifying now the p-value that this is larger. Our set score is still 2.97, but now it's basically to be calculated as 1 minus 0.9985, not multiplied by 2 because it's a one-sided hypothesis at 0.015. So there's now 0.015. This is 0.15 as our p-value. So we know now this is significantly rejected. So x bar is not smaller equal than mu. It's greater than mu with a probability of 0.15%. Good. So the sketching out makes a lot of sense. And I want to now quickly do this example here in R, and you have the R code on your canvas. I'm going to zoom in here a bit. Okay, so 7.29. So the problem here in R is a little differently to look at because we're actually doing something that R would usually do internally with functions. And these are considerably easy functions. But if you calculate it through, yes.
Did you click enter when you put your?
Yes, control and enter. Control and enter on 2 will clean the environment entirely. Then you can, with the first line that actually contains code, that's line 5, that's assigning the value of 500 to your object mu. Line 6 will assign hundreds to object sigma, and 542 to x bar on line 7. And 50 to n in line 8. So if you are, and this is again where we're going back to soft coding, hard coding, to assigning values to object with variable, and you can now define a new variable based on these variables that you have defined here on lines 5 to 8, 5 to 8. Yeah. So if I'm calculating now sigma, which is the standard deviation of 100, divided by the square root of n, this is our 100 divided by the square root of 50. So the SEM here is 14.14. If I want to calculate now my set, I basically calculate x bar minus mu, as we know, it's 542 minus 500, divided by the standard error of the mean. So our set is here 2.97. If I'm calculating now a p-value in a two-sided distribution, and this is a little bit more complicated. So we have here p-norm. P-norm is a little, it's not as easy to think about it, but if you do p-norm, so our set is 2.97. If we do p-norm, this is actually a function that allows for you to calculate your p-value, assuming a normal distribution. So what we're looking at in the distribution table, R can actually do for us with this function. And it basically, what it does with absolute, it basically takes out the negative sign. Whatever that sign is, it will always be positive. So if set would have been negative, it will take this negative sign, drop it, and will only take the positive. And it will now quantify by setting this negative here, no matter what. Okay, let's think about it. We always want this to be negative because we always want that tail to the left, right? So we're doing this now by setting set, whatever that calculation is, to positive, and with the negative sign, it will always be negative. So thereby we get, regardless of the value, we will always get a negative estimate for this set. And p-norm basically gives us for this negative set entry, the probability to the left. And this is how we can be working with it. So if we have now a p2 tailed, we essentially, we know this has to be 0.003, that's 0.3%, and that's our two-tailed p-value. It's identical to what we did in Excel, where we calculated our p-value here is 0.03. So it's that set, and this step is replaced by automatically querying it from a normal distribution. So R is basically creating that function. You remember how I showed you the normal distribution is nothing else but a mathematical function? R is taking this function and basically calculates it for you based on that function. Calculates the area under the curve for you. So this being said, so here we're rejecting the null hypothesis. So we're concluding that X bar is significantly different from our mu. In a one-tailed hypothesis, we're doing the same story. We're doing the same thing. So we're again calculating the p-tail, but this is smaller. P one-tailed smaller, that's our p-norm of set, which basically gives us everything below that. So now I don't have this absolute value story, because now I'm literally interested in the set. If this is negative, I want everything to the left, regardless of whether it's positive or negative. So I'm getting in this shape or form with this p-norm value, I get always the negative, everything to the negative, pointing towards the negative, so to the left. So here it is 0.9985, because I did not set it negative. So that's our P one-tailed for smaller.
Why do you have to copy and paste just the phenol and then do all of it? And then control enter all of it? But didn't you copy phenol and put it?
No, I didn't. No. This should be the same line 22 that you have in your code. Yeah?
No, it is, but I thought you copied it down there.
No, I didn't. It just looks the same. Oh, you mean, oh wait, a little higher.
Yeah.
This was just to show you what p-norm does. But basically it does the same here. Yeah, I'm switching back and forth with consort. Don't pay too much of that. I'm trying to explain it as we go. And sometimes I want to emphasize it to show it in the consort. Don't be confused about that, please. Okay, so the one-tailed hypothesis, if we're not interested in everything that's greater than one, we're basically, the research hypothesis sample is greater, the sample mean is greater than the population mean. So now we're taking 1 minus p norm. So now we're interested in that little tail above. So now we do 1 minus p norm. So that gives us the 0.14. So that's setting it to positive and then forcing it to be a negative value. You only do this for the two-tailed hypothesis because you only want to understand the tail. Only for the one-tailed hypothesis, you don't have to set it 0 and negative. And you have now in lines 34 and 35, you have the same calculation. X bar is here our mean, our sample mean. 1.96 multiplied by the standard error of the mean gives us now 95% confidence intervals, which are just as we calculated in Excel. 514 and 570. The effect size is calculated by, as we know, it's again X bar minus mu. We again need to set it absolute, because conventionally just the effect size is always positive. Hypothetically also can be negative, right? So if you don't put this absolute, it would be negative, but you consider it positive. Remember the convention, which is 0.2 to 0.5 is small, 0.5 to 0.8 is medium, and greater than 0.8 is large. So that's the effect size. The effect size is here 0.42, which represents a medium-sized effect size. So that's all the code for 729. That's all that's needed. And it's basically just utilizing RStudio as a calculator, nothing else. Okay, any questions to any of this code? No? I know it's a little much, but it's like play around with it if you're interested. See how you can reproduce your examples in Excel. Yes, please.
Will you have to send in for the end of the class?
Yes, please hand in, just like in the first lab, just hand in the console.
Like the R code?
No, the console printout.
Oh, okay, so it's from this, right?
Yep. Just, you can just, again, select everything, press Control and L. Delete everything in the console, then click on the script on top, press Command and A, and run the whole thing. It will, again, automatically run the whole thing, and then just copy the console output. And then again, it's STAT1021F, your family name, and then practice lab 2. Yes, please.
Well, what did we do with Excel before? We went through Excel. Are we submitting that also? Or
No, you don't need to submit.
that was just for us to learn?
Just, yeah. No, it's just, so the Excel example is just important because I want you to be very comfortable with these estimations, and one-sided and two-sided hypothesis, it's just important to kind of be able to recognize them and know how to compute them. And it's not impossible that you get something on the quiz, one-sided and two-sided. Yes, please. No. We're still doing 7:30 now. So we still have half an hour. We're doing 7:30 now. The second example that we did. Yeah, you can just rerun the code. That's no problem. Okay, so now we have the same example as we had last time. We're going now to 7:30. Same exercise. You're conducting a SAT test on a sample of 132 people for whom you observe the mean will respond the SAT of 490. The population mean is 500. Standard deviation is 100. So we have a sigma of 100 just in the other group. Mu is 500. X bar is now, as compared to the other one, it's 490. So it's smaller than the mu. Population mean 500, yes.
So sigma is the same as standard deviation?
Sigma is standard deviation. So please keep in mind, when you speak about the sample, your standard deviation is either S or there is S, SD, the typical sample standard deviation. If you have statistics or parameters from a population, you distinguish statistics come from a sample. Parameters come from a population. Parameters are with a Greek notation. This is either mu or sigma. Statistics are for standard deviation, it's an S or an SD. And for a mean, it is either M or X bar. These are the commonly found definitions. So we have here an X bar of 490, a mu of 500, an N of 132, and a sigma of 100. And that's important to keep in mind because this is a SAT test. So you need a sigma, and you need to be able to identify that this is a sigma and not an S. And the difference is here that it comes from the population. And this is because it's in the same sentence. The population mean is 500, the standard deviation is 100.
The population mean is mu.
Population mean is mu, the population standard deviation is 100. That's sigma. So we have sigma 100, mu 500, X bar is 490, and the N is 132. So in step one, we're defining our populations. We understand the populations. So the population is 132 people that are randomly sampled, and we're comparing it to the student population in the US with a mu of 500. Our null hypothesis in the two-sided test is X bar equals mu. Our alternative hypothesis is like X bar does not equal mu. Alpha is 5%. Our set here our set here is calculated, as we know, is usually from x bar, parentheses, x bar minus mu divided by standard error of the mean. Oh, that was pre-calculated already from last year. So the calculation of the standard error of the mean is of course B1, which is our sigma, divided by the square root of B4, which is our sample size, square root of the n. So our mu is 500. Our confidence interval is, and that's actually supposed to be x bar. Sorry, x bar is 490. Our lower limit of the confidence interval is 490 minus 1.96 multiplied by the standard error of the mean. And our upper limit is again 490 plus 1.96 multiplied by our standard error of the mean. That's 507. What we see already when we look at this, we see 472 multiplied by 507. So 472 to 507 includes our population mean. That means we're basically looking at a significant sample, non-significant sample. Sorry. Okay, in a two-tailed hypothesis, we know our null hypothesis x bar equals mu, whereas the research hypothesis x bar is unequal to mu. Our set is minus 1.14, which corresponds to a p of, this is where we're going to the distribution table, minus 1.14. That's here 0.1271. 0.1271. But we need to calculate it by 2. No. We need to calculate this twice. That gives us a p of 0.25. As a proportion, this is 0.25. As a percentage, this is 0.25 multiplied by 100, which is 25%. So we have a one left-tailed would then be basically quantifying everything to the left as the research hypothesis, everything to the right as the null hypothesis. So our null hypothesis here is x bar is greater equal to mu. Our research hypothesis x bar smaller than mu. The set is here the same. So is the p, but it's only 0. So this is now a one-sided p. So we're doing 0.12. I forgot it. 0.1271. So our p proportion is again 0.1271. And our p percentage equals this multiplied by 100. So again, the research hypothesis points the direction in which you're interested. So now here's actually negative. So I'm not going to make that mistake again. So we are now here. So we're taking the probability, this area under the curve, everything to the left of minus 1.14. If we do this for right-tailed, we have the opposite direction with x bar is smaller equal to mu. Our x bar is greater than mu as our research hypothesis. Set is again the same. Our p is now, this is where it's getting tricky now. So the p is now essentially directional, but it's everything greater than our actual set score. It's basically, it would be starting only from here, but it's basically everything above that. So this is now 1 minus
0.1271. So this is 87%. Make sense? We're not multiplying it by 2 because it's a one-tailed hypothesis, but it basically constitutes everything to the right. Proportion is the same. Now we're calculating this multiplied by 100, 87%. Good, so that's 730. Same example, we did it already in last class. Now we're going to bring it into R. We're having here the same list of entries with mu, sigma, x bar, n. Gives us exactly those 4. It's the same calculation. SM is here 8.7. Z is calculated as minus 1.14. And we are basically looking here at 0.25. It's the same calculation. Again, P norm is everything to the left, which is here 0.1252. It's actually, if you pay attention, it's actually smaller than what you get from the distribution table. It's actually more accurate because it takes the exact value. So don't be concerned if R gives you a more exact estimate, because it takes the actual function and it takes, I don't know how many decimal it takes into account. So this is how inaccurate basically distribution tables are by the nature of them. So we have now detailed smaller, and here we have greater, which is basically here 0.87. Our confidence intervals are again the same, with 473 to 507. Our effect size is here 0.1, so that's a small effect size. What would happen now if I wouldn't have studied 132 patients, but I would have studied 1,300 patients? Let's do this 1,320. So now all of a sudden, and that's interesting, and this is why soft coding is so nice, because you can basically simulate this things out. If I would have studied 10 times the number of patients, I would have firstly a smaller square root of the mean, standard error of the mean. This decreased now from 8.7 to 2.75. Logically, because the number of your sample is basically determining how much variability you see in your distribution of the sample means. If you have a large sample of 1,000 students, you have a more accurate estimate of your population mean. In addition to that higher level of accuracy, you also have less variability. You have less variability with those assumed hypothetically repeatedly drawn samples. And as a consequence to that, and this is what's coming back to what I said, the problem is with big data. If you have really large data sets, it's highly significant. So minus 3.63 is far beyond significance level. So that's the problem. And we are doing now another example. We have 15 more minutes. Yes.
How do we, so on R now, how do we save all those?
So you can save this by basically just, so you click, okay, once again, for the recording as well. This deliverable today is like, just like for practice lab 1, it's, you click on the console, you press Control and L. You click on the script up here. Anywhere in the script. You press Command and A, or Control and A for the Windows users. You select everything in the script, you press Control and Enter. Now you click in the console, you select everything in the console, you press Command and C, you go on the Spotlight and you look for text edit. You get a text editor open.
How do you select? It doesn't let me select everything in the console.
No, you need to go from the bottom and you need to select it by hand manually all the way up. Yes.
I can also copy and paste that into somewhere that I can change it into text.
You want to change it into what?
It doesn't have to go straight into the text that you put in,
Yes, as a text file, please. Yeah.
but if I can do it on another platform, I could just copy and paste it,
What is the other platform?
like Word, not Word, Google Docs, let's say download it as text. I can.
If you can save it as a rich text file, yes, I would prefer that. But so the problem is if you have it in Word, in an actual Word document, it will change the tabs and everything. So it's becoming illegible. That's why I prefer text document, but it's fine. You can also, you're on a Mac, you should have text edit. You can copy it from there. But it's fine. If you want to Google Docs, it's fine. Yes, please.
You did Command A and you did Command C and Command A.
No, I did Command A, Control and Enter, because that's how you run it. And then you select everything from the console and you copy that from the console into your text file. Okay. Yes, please save it then as, so you save this, you copy it and you save it as STAT1021, STAT1021F, family name, practice lab 2. Good. So that's how this is supposed to look like. Good. Okay, so back to Excel. Let's. Excuse me?
You just turn it into a PDF.
No, you save it as a text file, not as a PDF. Okay. So we're creating now a new worksheet in our document, and we're going to do a third example for the last 30 minutes. So that example is basically an example that I kind of like. So we're conducting a set test on a sample for which you observe a mean weight of 150 pounds. The population mean is 160, the standard deviation is 100. And this is now studying in more detail what I mentioned before. If you have a larger sample size, you're more likely to see a significant difference. So again, let's start off with defining mu, sigma, x bar, the n. So we have a sample of 30 people, as per example A. Oh no, mu. So sample size, let's do this a little different. A is n equals 30. Okay. So we have a mu of population mean is 160. We have a sigma of 100. We have an x bar of 150. Our n for the first example is, let's do a regular hypothesis testing. So we have a set to be, we do a standard error of the mean, which is now sigma divided by square root of the n, which is 18.257. Consequently, our set equals mu, no, x bar minus mu divided by standard error of the mean. So minus 0.54. So our p two-sided, for a set equals minus 0.55 is now two-sided p 0.55 minus 0.55 is corresponding of 547 actually. That's certainly more accurate. So we have minus 0.547, so that's 55 minus 0.55. We have here 55, this is here 0.2925. 12. So 12. So that's now 0.2912 multiplied by 2, right? So if we were interested now in a P1-sided set equals minus 0.55, where we assume that our null hypothesis is, the null here is that X bar is greater equal than our mu, then the research hypothesis would be X bar smaller than mu. Then our P would be 0.2912. So that P would be 0.2912. 0.2912. Because research hypothesis again determines which direction we're testing. We have a negative value. So everything less than the set will be in our research hypothesis. That's the P value we're testing. And that probability is just greater than 5%. So if we were to do the same analysis now with null hypothesis would be X bar smaller equals mu, and our research as X bar greater mu. So now we basically would calculate our P1-sided as 1 minus 0.2912. So that's 0.70, so it's even larger. If we're increasing now the sample size and our N is 300, if we are calculating now calculating the standard error of the mean, we're basically taking our sigma of 100, we're dividing it by square root of the N of 300. That gets us to 5.77, so it's substantially smaller, right? Our resulting set is now equals X bar minus mu divided by the standard error of the mean. And here was minus 1.73. So our P2-sided is now for minus 1.73. Is now, and this is like the example, has pretty much the same value, minus 1.73, that's here, 0.0418. So we need to multiply this by 2. We have a p-value of 8%. If it were a one-sided hypothesis test, we would basically look at a significant result now. So I'm not going to repeat the one-sided, but if we do C, and this is basically what I wanted to show. So we have now an N of 3000. We have an SEM of equals sigma divided by square root of the N. So now our standard error of the mean is only 1.8. The set is now an X bar minus mu divided by our standard error of the mean. This is now minus 5.477. Consequently, this is highly significant. Because the set is very much to the extreme and exceeds by far the 1.96 as the threshold. Okay,
You know what's significant why? The vertical threshold is 1.96.
96. For 5%, it would be 1.96. It's interesting if we, for example, would do here what we did for the other one. If we say this is a P one-sided now, so we have a null hypothesis now of X bar is greater equal mu. The research hypothesis of X bar smaller than mu. Then our P one-sided corresponding with our set score of minus 1.74 or 73 would here essentially be, and again, the research hypothesis drives which area under the curve you're interested in, is now 0.0418. So now it's actually significant with an alpha level of 5%. Because it's a one-sided hypothesis. If you revert the hypothesis and you say, okay, so my null hypothesis is actually X bar is smaller equal than mu, and the research hypothesis is X bar greater than mu, and my P one-sided is now the opposite, which is now equals, no, it's actually this. So 0.0418. It's 1 minus 0.418 is equal to minus. So this is equals 1 minus 0.0418. There's now 0.9582. So that's basically the key is really to understand in which direction you actually quantify the area under the curve. All right, any questions? Yeah, yes.
Where's already submitting the practice file?
Yes, just the practice lab, just copy this out, the text file, that's all that's needed.
So what's the difference between the because you're saying it was 1.96, but how is that different from the P? Because the P value isn't that less than like 5%, then it's like significant.
As soon as the P value is smaller than the alpha that you have defined, if you define this as 5%, then you would consider this as being significantly different. So then your sample mean is significantly different from your population mean. Yeah. All right, that's all I had. Thanks so much. Have a nice evening.
I just realized I just have this one. I didn't. Like I didn't copy.